On the 23rd of September, 1999, after a journey of more than 600 million kilometers and nearly 10 months through space, a NASA spacecraft arrived at the planet Mars and was never heard from again. The Mars Climate Orbiter was a real spacecraft built by real engineers, carrying real instruments to study the Martian weather. It cost with its companion mission hundreds of millions of dollars. It had flown flawlessly almost the entire way across interplanetary space. And in the final minutes, as it slipped behind Mars to begin slowing into orbit, it flew too low. Far too low. It dipped so deep into the thin Martian atmosphere that it was destroyed, burned, torn apart, or sent skipping helplessly off into deep space. And here is the reason. The reason is so small and so human that when NASA announced it, the world almost did not believe it. The spacecraft was lost because two teams of engineers, working on the very same mission, building the very same spacecraft, were quietly speaking two different languages of measurement. One team worked in metric units, one team worked in imperial units, and a stream of numbers passed every day between them, numbers that looked perfectly correct and meant something different to the sender than to the receiver. No one ever converted them. And so a spacecraft flew across the solar system and arrived at Mars carrying, buried in its mathematics, a silent mistranslation. This is the story of the spacecraft, lost in two languages. To understand how the Mars Climate Orbiter was lost, you have to understand the philosophy that built it, because that philosophy is part of the story. In the 1,990 seconds, NASA was operating under a guiding idea strongly associated with its administrator at the time, Daniel Goldin. The idea was summed up in three words: faster, better, cheaper. For a long time, robotic space missions had been enormous, expensive, decade-spanning projects, single gigantic spacecraft that cost so much that the loss of one was a national catastrophe. Faster, better, cheaper was a deliberate move away from that. The idea was to fly more missions, smaller and less expensive, more often, to accept that some would fail, but to get far more science done per dollar by not putting everything into a few colossal, irreplaceable spacecraft. The Mars Climate Orbiter was a child of that philosophy. It was part of a relatively low-cost pair of missions to Mars: the Climate Orbiter, which would study the Martian atmosphere and weather from orbit, and the Mars Polar Lander, which would touch down near the Martian South Pole. The missions were run on tight budgets with tight schedules and with lean teams. And lean budgets and schedules, as we will see, have a way of thinning out exactly the kind of careful, redundant checking that catches a quiet mistake. Now, the Mars Climate Orbiter was not built by NASA alone, in one building, by one team. Like almost all large spacecraft, it was a collaboration, and two organizations, in particular, matter for this story. The spacecraft itself, the physical hardware, was built by the aerospace company Lockheed Martin at its facility in Colorado. And the navigation of the spacecraft, the work of tracking exactly where it was in space, and computing the commands to guide it accurately to Mars, was carried out by a navigation team at NASA's Jet Propulsion Laboratory, the famous JPL, in California. So you had two centers of work: Lockheed Martin in Colorado, who built the spacecraft and operated some of its systems; JPL in California, who navigated it. And these two teams had to work together, constantly, throughout the mission. Information had to flow between them. A steady daily exchange of numbers describing what the spacecraft was doing and where it was going. Two teams, two organizations, two institutional cultures, and, as it turned out, two different default systems of units. The Lockheed Martin side and the JPL side were not, in one crucial respect, speaking the same language, and the mission had not built a reliable translator between them. Now I need to give you the central technical idea of this whole episode, and it is an idea about navigation, about how you steer a spacecraft across hundreds of millions of kilometers. You might imagine that navigating to Mars is mostly about the big rocket burns, the great firings of the engine that set the spacecraft on its path, and those matter. But there is something subtler, and for this story, far more important. A spacecraft in flight is not perfectly undisturbed. It is constantly subjected to tiny forces. Sunlight itself pushes on the spacecraft, the gentle pressure of photons striking its surfaces and its large solar panel. The spacecraft also has to fire small thrusters regularly, in little puffs, to control its orientation, to keep its antenna pointed at Earth and its instruments aimed correctly. Each of those little thruster firings, besides turning the spacecraft, also gives it a tiny nudge, a small push that very slightly changes its path. Individually, these forces are minuscule, but they act continuously for months, and over a journey of 10 months and 600 million kilometers, a vast number of tiny nudges, all added up, can move a spacecraft a very long way from where it would otherwise have been. So the navigation team must keep careful track of all these small forces. They must know about every nudge, account for it, and continuously correct the spacecraft's predicted path. And to do that, the navigators needed data about those small forces from the spacecraft systems. They needed, in particular, a regular accounting of the little pushes delivered by the orientation thrusters. And that accounting was the stream of numbers in which the disaster was hiding. So let us talk about the two languages, the two systems of units, because the gap between them is the quiet hinge of this entire story. Around the world, science and engineering use overwhelmingly the metric system, more formally, the International System of Units, the SI system. In the metric system, the unit of force is the Newton. But in the United States and much of engineering practice, an older system is still widely used, the imperial or US customary system. In that system, the unit of force is the pound force, what people usually just call a pound when they are talking about a push or a weight. Now, a Newton and a pound force are both perfectly valid units of force. They simply measure the same physical thing, a push in different sizes. 1 pound force is equal to about 4.5 newtons. So a force of, say, 1 pound force and a force of 1 newton are not the same push. The pound force is the bigger unit by a factor of roughly 4.5. If you have a real physical force and you describe it in newtons, you get one number. If you describe that very same force in pounds force, you get a different smaller number, smaller by that factor of about 4.5. Same push, two unit systems, two completely different numbers. Now, the quantity that actually mattered for the Mars Climate Orbiter was slightly more than a plain force, and the detail is worth getting exactly right. The navigators needed to account for the effect of the small thruster firings, and the natural way to measure the total effect of a thruster firing is a quantity called impulse. Impulse is, in essence, a force multiplied by the length of time it acts. A small thruster firing for a brief moment delivers a certain impulse, a certain total nudge to the spacecraft. And impulse, being built out of force, also comes in two unit system flavors. In the metric system, impulse is measured in Newton seconds. In the imperial system, it is measured in pound seconds, sometimes called pound force seconds. And because a pound force is about 4.5 times bigger than a Newton, a pound second of impulse is about 4.5 times bigger than a Newton second of impulse. Here then is the precise shape of the trap. A piece of software on the spacecraft side, built by Lockheed Martin, produced figures describing the impulse from the small thruster firings. Figures used in a file that the JPL navigation team relied on. That software produced its impulse figures in imperial units, in pound seconds. But the JPL navigation software that received and used those figures was written to expect metric units. It expected Newton seconds. And nowhere in between did anything convert one to the other. So picture exactly what happens when that data flows. The spacecraft side software computes the impulse of a small thruster firing, and the true answer, in imperial units, is some number of pound seconds. It writes that number into the file. The navigation software opens the file, reads that same number, and because it was built to expect Newton seconds, it interprets that number as Newton seconds. But a pound second is about 4.5 times bigger than a Newton second. So when the navigation software reads a figure that genuinely represents, say, 1 pound second of impulse and treats it as 1 Newton second, it is treating a real push as though it were only about a fifth as large as it truly was. The number passed across perfectly intact. Not a single digit was corrupted. The file transferred flawlessly. But the meaning of the number, the unit attached to it, did not survive the journey. The sender meant pound seconds. The receiver heard Newton seconds. And so, every time the navigation software accounted for one of those small thruster nudges, it used a value that was wrong. Too small, by a factor of about 4.5. The spacecraft was being navigated with a systematic, repeating underestimate of the forces acting on it. Not a random error, a consistent, one-directional mistranslation applied over and over, all the way to Mars. So the Mars Climate Orbiter launched in December 1998 and began its long cruise toward Mars. And from early in that cruise, the silent mistranslation was at work. Every time the navigation team accounted for the small forces from the orientation thrusters, they were using values that were too small. The error was steady, and it was always in the same direction. Now, here is something genuinely important, and it is the reason this story is not just a tale of one bad number. The error was, in fact, producing visible symptoms during the cruise. The spacecraft's actual path was not quite matching the navigator's predictions. When the navigation team tracked the spacecraft using radio signals to measure precisely where it was and how it was moving, they could see small discrepancies. The spacecraft kept turning up slightly off from where their model said it should be, and the team had to keep making corrections. There was a sense, among some of the people working the mission, that something about the navigation was not fully understood, that the spacecraft was not behaving exactly as the models predicted. The symptoms were there. The drift was real, and it was visible in the tracking data. But the symptoms were small, and the cause was not identified. The discrepancy was noticed and discussed and worked around with corrections, but the underlying reason, the unit mismatch buried in the flow of impulse data, was not caught. Why was the cause so hard to find when the symptom was right there in the data? This is worth dwelling on because it is the genuinely instructive part. The discrepancy in the spacecraft's position was small. Across the vast distances of interplanetary navigation, a small, slowly accumulating error does not look like an alarm. It looks like the ordinary expected imperfection of modeling a real spacecraft. Navigation always involves small mismatches between prediction and reality. The universe is messy, the models are approximations, and the navigators expect to make regular corrections. So a small persistent drift did not automatically scream unit error. It blended in with the normal noise of the job. And there was a deeper organizational reason. The mismatch lived in the seam between two teams. The faulty numbers were produced by software on one side, the spacecraft builder's side, and consumed by software on the other, the navigation side. Neither team had the full picture in one place. The people who knew intimately what units the spacecraft side software produced were not the same people who knew intimately what units the navigation software expected. The error did not live inside any one person's work, where they might have caught it. It lived in the gap between two groups, and gaps in a large project are exactly the places where no one is quite responsible, and where a quiet mistake can survive. There were also, the later investigation found, missed opportunities. Moments when concerns about the navigation were raised, and the process for tracking and resolving those concerns did not function well enough to drive the problem to ground before it was too late. So the cruise continued for nearly 10 months, with the small steady error quietly bending the spacecraft's path. And the navigation team kept correcting for the visible drift without knowing its true source. As the Mars Climate Orbiter approached the planet, the navigators were preparing for the most critical event of the entire mission. The moment the spacecraft would arrive at Mars and be captured into orbit. To be captured into orbit around a planet, a spacecraft has to slow down, and the Mars Climate Orbiter was designed to slow down using a clever and economical technique. It would fire its main engine to slow itself somewhat, and then, crucially, it would dip into the upper edge of the Martian atmosphere and use the drag of that thin air to bleed off speed. The atmosphere itself would act as a brake. This technique is real, and it is used. It saves an enormous amount of fuel compared to braking with the engine alone. But it depends absolutely on flying at the right altitude. Dip into the atmosphere at the right height, and the air slows you gently and safely into orbit. Dip too low into denser air, and the drag and the heating become destructive. The whole maneuver hinged on the spacecraft arriving at Mars on a path that would carry it through a precise narrow band of altitude. And the navigator's picture of that path had been bent, the whole way from Earth, by a force they had been steadily understating. So now we reach the question at the heart of this story. How does a small, steady error in a minor force, the little nudges from orientation thrusters, turn into a spacecraft that flies fatally too low at Mars? The answer is one of the most important and most beautiful ideas in all of navigation, and it is the idea of accumulation. Let us build it carefully. The error in any single thruster nudge was tiny. The mistranslation made each little push look about 4.5 times smaller than it really was, but each little push was minuscule to begin with, so the error per event was utterly negligible, nothing. But here is the thing about navigating across interplanetary space. The journey is enormously long in both distance and time. The Mars Climate Orbiter cruised for nearly 10 months. Over that time, the orientation thrusters fired again and again and again, a great many times. And every single one of those firings carried the same small error, always in the same direction. The errors did not cancel out. This is the crucial point. If the errors had been random, sometimes too big, sometimes too small, they would have largely averaged away to nothing over a long journey. But a unit mismatch is not random, it is systematic. Every firing was understated by the same factor in the same direction, so the errors did not cancel. They added. They accumulated. A tiny error, repeated consistently, and added up over 600 million kilometers, grows into a large one. Let me make the difference between random and systematic error completely concrete, because it is the whole mechanism of this disaster. Imagine you are walking, blindfolded, trying to go in a straight line. If your errors are random, a small accidental veer left, then a small accidental veer right, unpredictably, then over a long walk, those veers tend to partly cancel. You will wander a bit, but you will stay, very roughly, near your intended line. The errors fight each other. But now imagine your errors are systematic. Imagine that every single step you veer left by the same tiny amount, a barely perceptible bias, always in the same direction. Over one step, you would never notice it. Over 10 steps, still nothing, but over 10,000 steps, that consistent tiny leftward bias added up has carried you enormously far from where you meant to be. You could end up facing a completely different direction. That is the difference random errors cancel. Systematic errors accumulate. The unit mismatch on the Mars Climate Orbiter was the purest possible systematic error. Every thruster firing biased the same way by the same factor. And so, like the blindfolded walker, with the consistent veer, the spacecraft was carried, slowly, steadily, invisibly, over hundreds of millions of kilometers, off its intended line. By the time it reached Mars, the accumulated drift had moved its predicted arrival path by a serious, dangerous amount. So here is what the accumulated error did to the arrival at Mars. The navigation team, using their data, had a prediction for the path the spacecraft would follow as it approached the planet, and in particular for the altitude at which it would skim the Martian atmosphere during the braking maneuver. Their plan called for the spacecraft to pass Mars at a safe altitude, high enough that the thin upper atmosphere would break it gently. The intended closest approach was at an altitude of something like a couple of 100 kilometers above the Martian surface. But the navigator's picture was wrong because it had been built the whole way from Earth using the understated forces. The true path of the spacecraft was different from the predicted path, and the difference was in the dangerous direction. The accumulated error meant the spacecraft was actually going to pass much closer to Mars than the navigators believed. Instead of skimming the atmosphere at a safe altitude of around a couple of 100 kilometers, the Mars Climate Orbiter was, in reality, on a path to pass at an altitude far lower than that. Low enough to carry it deep into denser atmosphere, far below the altitude any safe braking maneuver could survive. The navigators were steering a spacecraft toward a safe corridor. The spacecraft carrying the silent error was actually aimed below it. So let us actually write down the equation, the chain of relationships that lost the Mars Climate Orbiter. At the foundation is the most famous equation in all of mechanics, Isaac Newton's second law, and the form of it that matters here is the form involving impulse. It says this: the impulse delivered to an object, the force multiplied by the time it acts, equals the change in that object's momentum. Impulse equals change in momentum. In plain terms, a push applied for a span of time changes how the object is moving. The bigger the impulse, the bigger the change in motion. So when the navigation software accounted for a thruster firing, it took the impulse of that firing and used it through this law to update its picture of the spacecraft's motion and position. The impulse went in, a change in the predicted trajectory came out. The law itself is perfect. Newton's second law did not fail anyone. The equation was not wrong, and it was not missing, and it was not difficult. What was wrong was the number fed into it. The impulse value the navigation software used was every time too small by a factor of about 4.5, because it was a figure that genuinely meant pound-seconds, being read as Newton seconds. Now here is the idea I most want you to carry away from this episode, and it is the same deep idea at the heart of our story about the Gimli glider, the airliner that ran out of fuel. A number on its own is not a physical quantity. A number becomes a physical quantity only when it is married to a unit. The bare figure that passed between the two teams was not by itself an impulse. An impulse is a number and a unit together, so many Newton seconds, or so many pound seconds. The unit is not a label stuck on afterward. The unit is half of the very identity of the quantity. When that bare figure traveled from the spacecraft side software to the navigation software, the number traveled and the unit did not. The unit was never written into the data. It lived only in an assumption in the mind of each team about what the numbers in that file meant. And the two teams held different assumptions. The senders assumed pound seconds. The receivers assumed Newton seconds. Newton's second law, impulse equals change in momentum, cannot detect that. An equation has no way of knowing what units you intended for the numbers you give it. It takes the number and it returns a result faithfully, blindly. The equation will compute with a pound seconds figure exactly as readily as with a Newton seconds figure. The meaning, the unit, the truth of what the number stands for, all of that lives entirely outside the equation, in the human understanding around it. And on the Mars Climate Orbiter, that understanding was split in two, and no one had bolted the two halves together. So let us assemble the full chain of the disaster in order. First, the spacecraft side software correctly computed the impulse of each small thruster firing in imperial units in pound-seconds. That computation was correct. Second, those figures were placed into a data file as bare numbers, with the unit living only in the builder's assumption. Third, the navigation software read those figures and interpreted them as metric as Newton seconds. So it treated every impulse as about 4.5 times smaller than it truly was. Fourth, through Newton's second law, the navigation software used those understated impulses to update the spacecraft's predicted path. Each update carried a small systematic error. Fifth, over nearly 10 months and a great many firings, those systematic errors accumulated. They did not cancel because they were all biased the same way, and the predicted path drifted steadily away from the spacecraft's true path. Sixth, the spacecraft arrived at Mars on a true path far lower than the navigators believed, aimed beneath the safe atmospheric corridor. Every step in that chain except one was performed correctly. The impulse computation was right, Newton's law was right, the file transferred perfectly. The arithmetic was flawless throughout. One thing failed: the unit of a number was assumed differently by the team that wrote it and the team that read it. And that single silent mistranslation, propagated faithfully through a chain of correct mathematics and accumulated across 600 million kilometers, was enough to lose a spacecraft at another planet. So let us go to the arrival on the 23rd of September 1999 with the equation in hand. The Mars Climate Orbiter approached the planet. The navigation team, working from their drifted picture, believed the spacecraft was on a safe path. In the days before arrival, there had in fact been discussion within the navigation team about the spacecraft's trajectory, and some unease about how low it might be coming in. There were opportunities in those final days to act on that unease, to compute and command a final correction maneuver to raise the path. But the situation was not fully understood, the concern was not driven to a clear resolution, and a possible final trajectory correction that might have lifted the spacecraft to safety was not carried out. So the Mars Climate Orbiter flew on toward the planet on its true path, the path aimed below the safe corridor. As planned, the spacecraft fired its main engine to begin slowing into orbit, and then passed behind Mars as seen from Earth, which cut off radio contact, an expected, normal part of the sequence. The flight controllers on Earth waited for the spacecraft to emerge from behind the planet and re-establish contact. It never did. The Mars Climate Orbiter passed behind Mars and was never heard from again. What happened to the spacecraft itself in those final minutes behind Mars is understood from the analysis that followed. The Mars Climate Orbiter, on its true path, passed far too low over the planet, dipping to an altitude deep within the Martian atmosphere, far below the altitude any safe braking maneuver could survive. At that low altitude, the atmosphere, though still thin by Earth's standards, was dense enough to subject the spacecraft to severe drag and severe heating, stresses far beyond what it was built to endure. The spacecraft was, in all likelihood, destroyed, torn apart, or burned up by the atmospheric stresses. If by some chance it survived the passage structurally, it would have been so slowed and so disturbed, or conversely sent skipping on such an altered path, that it could not enter its intended orbit. It would have been lost regardless, tumbling away from Mars into deep space silent. Either way, the outcome was the same. The mission was over. A spacecraft that had flown perfectly for nearly 10 months and 600 million kilometers was gone in its final minutes at the destination, and the cause was a discrepancy that, in plain physical terms, came down to one number, meaning one thing to one team, and another thing to another. Hundreds of millions of dollars, years of work, an entire scientific mission, ended by a silent mistranslation. And here is a part of the story that makes it sting all the more. The Mars Climate Orbiter had a sibling. The same faster, better, cheaper program had sent a second spacecraft to Mars at almost the same time, the Mars Polar Lander, designed to touch down near the Martian South Pole. The Polar Lander arrived a few months after the Climate Orbiter was lost, in December 1999, and the Mars Polar Lander was also lost. Contact with it was never established after its descent toward the surface. Its loss was investigated separately, and the most probable cause identified was a different fault entirely, unrelated to the unit error, most likely a spurious signal that caused its descent engine to shut down early, while the lander was still high above the surface. So in a single year, NASA lost both of its Mars missions, back-to-back, to two separate failures. The double loss was a severe blow. It led to deep, painful organizational soul-searching. about the faster, better, cheaper philosophy itself, about whether the drive to make missions cheaper and faster had cut the budgets, the schedules, the staffing, and the checking too far. The Mars Climate Orbiter was not, in the end, only a story about units. It was a story about a way of working that had thinned out the margins, including the margin of careful, redundant checking, until a quiet mistake could slip all the way through. After the loss, NASA convened an investigation board to determine what had happened to the Mars Climate Orbiter. And the board's central finding became one of the most famous and most quoted conclusions in the history of spaceflight. The root cause of the loss was the failure to use metric units in the coding of a piece of ground software, the failure to convert between the imperial units, the pound-seconds, in which certain thruster impulse data was produced, and the metric units, the newton-seconds, in which the navigation software expected it. A spacecraft had been lost at Mars because a unit conversion that should have happened somewhere in the flow of data between two teams simply never did. When that finding was made public, the reaction was a kind of worldwide disbelief. It seemed impossible that an organization as sophisticated as NASA, on a mission of this cost and complexity, could be undone by something that sounds like an error from a school exercise. But here is the crucial thing the investigation made clear, and it is the honest and important part of the story. The unit mismatch was the trigger. It was not, by itself, the whole cause. The investigation board was emphatic on this point, and it matters. A single error, like a unit mismatch, should never be able to destroy a spacecraft on its own. A well-run mission is built with layers of defense, with checks and cross-checks and reviews, and processes for catching and resolving exactly this kind of mistake before it becomes fatal. The board's deeper finding was that those layers on this mission had not been strong enough. The unit error existed, but the real failure was that the mission's checking and verification process did not catch it across all the months it had to. The navigation discrepancy had been visible in the tracking data, and the concerns that some team members felt about it were not driven to a clear resolution. The communication between the navigation team and the spacecraft team across that organizational seam was not robust enough. The processes for surfacing a worry and forcing it to be understood and fixed did not function well enough. And underlying all of it was the pressure of faster, better, cheaper, the lean budgets, the lean staffing, the tight schedules, which left less slack for the deep, redundant, skeptical checking that catches a quiet mistake. So the lesson the board drew was not simply use metric units. The lesson was about defense in depth, about building a process strong enough that no single error, however small, however human, can run unchallenged all the way to a planet. The unit mismatch was the thing that went wrong. The thinness of the checking was the reason it was allowed to matter, and out of that loss came real, lasting change. The Mars Climate Orbiter, together with the loss of the polar lander, forced a serious reckoning. The faster, better, cheaper philosophy was re-examined, and the balance shifted toward giving critical missions the budget, the schedule, and the staffing needed for thorough verification, and toward not cutting the margins of checking so close. More specifically, the importance of clear, enforced standards for units became a permanent and emphasized lesson. The discipline of stating units explicitly, of converting deliberately and verifiably at every interface, of never letting a bare number cross between systems with its unit living only in an assumption. That discipline was reinforced, hard across the profession, and the broader principle that the interfaces between teams, the seams between organizations, are where errors hide and must be checked with special care, became one of the most cited lessons of the whole affair. NASA, of course, went on. In the years that followed, it landed rover after rover on Mars, and placed orbiter after orbiter successfully around the planet. The exploration of Mars did not end with 1999. It became, if anything, one of the great successes of modern spaceflight. But the Mars Climate Orbiter remained a permanent, almost legendary cautionary tale. Taught everywhere about the catastrophic power of a number whose unit was left to assumption. The loss of the Mars Climate Orbiter is now, in engineering and science education worldwide, one of the most widely told case studies that exists. It is taught in software engineering as the defining example of an interface error, of what happens when two systems exchange data while holding different assumptions about what that data means. It is taught in systems engineering as the classic case of a failure living in the seam between two teams, and of the special danger of organizational interfaces. And it is taught in physics and engineering classrooms everywhere as the single most memorable warning about units, about the absolute necessity of attaching, stating, and converting units with discipline. All of those readings are true. But here is the thing about the Mars Climate Orbiter that I find most haunting, and it is the thing that connects it to every other story on this channel, and it makes a fitting end to this run of episodes. On this channel, the most common pattern has been the missing equation, the Vasa-Tacoma Narrows, the Millennium Bridge. In each, the mathematics that would have explained the disaster did not yet exist, or lived in another field, or was known and ignored. The catastrophe came first, and the understanding followed, written in the wreckage. But the Mars Climate Orbiter, like the Gimli glider before it, belongs to a different and in some ways more unsettling family. The equation was not missing. Newton's second law, impulse equals change in momentum, is more than 3 centuries old. It is one of the most thoroughly known equations in the whole of human knowledge. Every engineer on that mission knew it perfectly. The disaster did not come from not having the equation. It did not come from the equation being hard. It was not hard. It came from feeding a perfectly good equation a number whose unit had been silently mistranslated, and from a process too thin to catch the mistranslation. Every disaster on this channel teaches us something about the relationship between mathematics and the world. And the Mars Climate Orbiter teaches perhaps the humblest and most chilling lesson of all, that having the equation and even computing it flawlessly is not enough, because the equation only ever processes numbers. The meaning of those numbers, the units, the truth of what they stand for, lives outside the equation in fragile human understanding. And if that understanding is split between two teams who never reconcile it, then the most perfect equation in the world will carry the error faithfully and without complaint all the way to another planet. I want to leave you with the thought I find most profound about the Mars Climate Orbiter, and it is the reason this story belongs on this channel, and a fitting note to close on. We tend to believe that mathematics is a universal language, that an equation is the same everywhere, that numbers are pure and culture-free, that if the math is right, meaning is guaranteed. The Mars Climate Orbiter is the gentle, devastating proof that this is not quite true. An equation is universal. Newton's second law is the same on Earth and at Mars, the same for every engineer who has ever lived. But a number flowing through that equation is not pure. A number is only meaningful when it is joined to a unit, and a unit is, in a sense, a human convention, a choice, newtons or pounds, kilometers or miles. Metric or imperial. The equation is universal, but the units are a language, and like any language, they can be spoken differently by different people, and a sentence can be mistranslated between them. The Mars Climate Orbiter was not lost because the universe is hard to predict. The universe held up its end perfectly. Newton's law worked flawlessly the entire way. It was lost because between two rooms of brilliant people, a number was passed in one language and read in another, and no one stood in the doorway to translate. The deepest lesson of every story on this channel, in the end, is some version of this. The mathematics of the world is faithful and indifferent and exact. It will always run. It does not care about our deadlines, our budgets, our assumptions, or our hopes. And so the entire burden falls on us, on the fragile, human work of making sure that the numbers we hand the equations are true, that the units are stated, that the meaning survives every journey between every two minds. The equation will never let us down. We can only ever let down the equation. The Mars Climate Orbiter is gone, somewhere at Mars, or scattered into deep space, lost in 1999. But the missions that came after it have flown and landed and orbited with extraordinary success, and they carry, in their procedures and their discipline, the hard lesson of the spacecraft that did not make it. The units are stated now, the interfaces are checked, the translation happens. The spacecraft was lost in two languages, because a number meant one thing to the team that wrote it and another to the team that read it, and the conversion that should have stood between them was never there. Strange equations are not always strangers. The strangest thing of all may be this, that the equation can be the most familiar one in the world, 3 centuries old, known to everyone, computed perfectly, and a spacecraft can still be lost, because the equation, for all its power, can only ever know the numbers and never the meaning we forgot to attach to them. The mathematics ran on schedule the whole way to Mars. It always would have. We simply, in 2 rooms, on one mission, forgot to agree on what our numbers meant. If you enjoyed this one, the story of the Vasa, a great warship that sailed barely 1,000 meters into its maiden voyage in 1628, and immediately fell over and sank because of an equation about floating that would not be written for another 100 years, is where this channel began, and a good place to begin again. Strange Equations is here for the math behind the moments that nobody at the time was calculating. If that is your kind of channel, subscribe. Thank you for watching.